All right, so this is going to be 14.7, finding maximums and minimums. So if you remember from Calc 1, the way that we used to find maximums and minimums would be two different ways. So one of the things that we want to take a look at is something called critical points. So these critical points or critical numbers, which are the x values, we found them using two different ways. So you either take the derivative, set it equal to 0, and solve for the values of x, or you found whenever the derivative is undefined. So if the derivative was undefined somewhere, then in that case, you could have a potential critical point there. All right, so some examples would be if you had like 1 over x equals 0, if this was a derivative, for example, then in that case, at x equals 0 would be when this derivative is undefined. So x equals 0 would be a critical point. All right. So not much has changed in 3 dimensions. So like in a multivariable function. Our critical points are still found using the derivative and where it's undefined. So in this case, because now we have two derivatives, it would make sense for us to find critical points wherever the partial derivatives are equal to 0. So in order for me to find a critical point, I would need to set both the partial derivative with respect to x and the partial derivative with respect to y equal to 0. Okay, so both of these guys have to equal to 0. And what we would need to do is solve a system of equations. So sometimes this gives us a system of equations. And we would need to solve this particular system. All right. Now, f sub x and f sub y does not exist. That is also could be a possibility. Or just how I have it here, I could have easily had it like 1 over xy, and then x and y would both be critical points. All right. So now here we do have a couple of things to kind of settle. Now that we are dealing with surfaces, we have some complexities here. So we're still going to call these local maximums and local minimums. So you can see that this is still a maximum and a minimum, but it's not the absolute maximum and minimum, right? So we call them local because our absolute maximum is all the way up here. Our absolute minimum is all the way down here. So even though this is the maximum, it's not the biggest maximum out of all of them. Okay, same thing here. This is our minimum, right? This is our minimum, but we have an absolute minimum. So when we talk about absolute extrema, okay, so absolute extrema, usually what we're going to do is we're going to bound this. So that will be a little later. So to find absolute maximums and absolute minimums, we will talk about them a little later. So these guys later, we will talk about them. And what we really want to focus on is these local maximums and local minimums. Okay, so let's just go ahead and read this part. So a function of two variables has a local maximum at a comma b if f of x comma y is less than or equal to f of a comma b, where xy is near a and b. So basically this a and b is considered to be a maximum. So remember the f's values are your y values, right? So remember f of x comma y is just your y's. Oh, in this case your z's, I'm sorry. Still in 2 dimensions. So basically this is saying that within a neighborhood, right, within some values of x and y that are near a and b, this value a and b tends to be much greater than the ones that are near it, which makes it a maximum. All right. Same thing happens. I swap the inequality. That means that any values near f of a comma b, if f of a comma b is much smaller than any of the other values near it, is going to be a minimum. Okay. So that's where that part is at, minimum. Okay, so this is pretty straightforward. It just kind of gives you a definition of what a local maximum and a local minimum is. So if the inequalities hold for all points x and y in the domain of f, then f is the absolute maximum or absolute minimum at a and b. Okay, so here we're looking just locally, some values that are near those points. But if it turns out that all the points satisfy that, then it'll be the absolute maximum or absolute minimum. So here's an example. So this one, I gave you the picture of this paraboloid, this elliptic paraboloid, and you can see that this guy is actually the lowest value in respect to all of these x and y values. So not only is this a local minimum, it's also the absolute minimum because it's the lowest of the low. You cannot, there's no point that's lower than this. So let's go ahead and practice. Let's just find some critical points, okay, from this guy. So let's practice finding some critical points. Remember, in order for me to find a critical point, I would have to take two partial derivatives. So I'm going to start off by taking the partial derivative with respect to x, right? And this is going to give me 2x. That goes away, minus 2, and then that's it. Now I'm going to take the partial derivative with respect to y. That'll be 2y minus 6. And also set this guy equal to 0. Because that's how we find critical points. We take the derivative, set it equal to 0. So in this case, here we have 2x equals 2. So x equals 1. 2y equals 6. So y equals 3. So you can see that the x value would be 1 and the y value would be 3. So here we didn't quite have a system of equations. These guys kind of solved itself. So you have 1 and 3. Now, since remember, we are in the xyz plane, so we would require to get that z value. That z value is super easy because remember, our z value is just our f of x value. So we're going to evaluate 1, 3 into our function. So you're going to get 1 squared plus 3 squared minus 2 times 1. Minus 6 times 3 plus 14. And you'll see that this one's going to actually give you 4. So my point is 1, 3, and 4. This is my point. All right. So now that's what we get. Now here is the other strategy. How exactly would we classify this as a maximum or minimum? Because we see the graph and we're like, well, this is clearly a minimum, right? Because if we have our graph, it's really easy to point out that this guy's going to be a minimum. All right. But sometimes it's not as easy. So what we did in Calc 1 is that we had some x values, some potential x values like x equals 1 and x equals 3. And what we did was we plugged in points. We plugged in points, and if it was positive, then negative, and then positive, we can easily see, oh, this is positive and this is negative, so this might be a maximum. Then it's negative and then it's positive. That's going to be a minimum. Okay. Now, the problem here is that now we have this x and y. So maybe plugging in points isn't going to help us very well. So this is in the single variable calculus case. So how would we classify this point as a maximum and a minimum without having to graph it? Okay. Now, well, it turns out that maximums and minimums are actually not going to be the only types of points that we have. So we also have some other weird shapes. So here's an example of a hyperbolic paraboloid. So let's go ahead and take a closer look at what exactly this looks like. Especially, we're going to look at the point 0, 0. 0, 0, and then comma 0. Okay, so let's take a look at y squared minus x squared. So I'm going to go here, and I'm going to have z is equal to x squared minus y squared. I think that's what I wanted. Or maybe it was the opposite. I forgot. It was this minus x squared. Was it that? Yes, okay. So we're going to take a look at the point 0, 0. So 0, 0. Oops. All right. So let's take a closer look at this. And you can kind of see that if I take a look at this particular point, it kind of looks like it's a maximum, right? At 0, 0, it kind of looks like, I'm sorry, it kind of looks like it's a minimum because it's the lowest point. But if I kind of turn it around, oh, well, now it's a maximum, right? So you can see that it switches from maximum all the way to minimum. So these types of points are what we call saddle points. So, and they also need to be classified. So not all critical points are going to be extreme values. Some of them can be something that we call saddle points. And maybe you have seen this in Calc 1, but we actually did encounter some saddle points. So, for example, y equals x cubed, if we were to take the derivative of that, or let's look at the graph, what we would end up getting is a critical point at x equals 0. So, or a critical number at x equals 0. But you can see here that this one is neither a maximum or a minimum. It's actually a saddle point. So we did kind of look at those types of problems, and you also have other problems where you can take the derivative and they kind of look like this, right? So here you also have like a saddle point that kind of looks like a maximum here and a minimum up here. So you do encounter these types of problems in a single variable case, and you will encounter them as well in multivariables. So we basically have three different types of critical points. Okay, so we can have either a minimum, we can either have a maximum, and we can have something that's not an extreme value. It'll be a saddle point. Okay, remember this is not extreme value. Okay, it's not an extrema. All right, so what we're going to do is something called the second derivative test. Now, I'm not going to derive this for you because it's pretty crazy, and it does involve a little bit of linear algebra, in which not a lot of you guys have taken. So this is basically what the second derivative test does for you. So suppose the second partial derivatives of f are continuous on a disk with center AB. And suppose that f sub x of a comma b equals 0 and f sub y of a comma b equals 0. Okay? So in other words, if I were to plug in a and b into my partial derivatives, I get 0. So therefore, it's a critical point. And now we're going to define another type of formula. So the second derivative with respect to x multiplied by the second derivative with respect to y minus the mixed partial squared. So this guy is going to be, so if this d, we call it the value of d, if the value of d is positive at this particular point, and the second derivative with respect to x is also positive, then the function evaluated at that particular point is a local minimum. Okay. If d is positive and the second derivative with respect to x is negative, then f sub a comma b evaluated at that point is a maximum. And if d is negative, regardless of whatever the second derivative of x is, it doesn't matter, it's going to be a saddle point. Okay. Now the only thing is that if d is equal to 0, the test is inconclusive. So we have to do something else. We might have to use technology or the level curves to kind of try to figure out what's happening. All right. So this is going to be the formula that's really going to help us figure out what it is. And notice that a lot of it, like if you kind of neglect this value of d, this is very similar to the way that we classified whether something was concave up or concave down, right? So remember, if you had f sub x, oh, I'm sorry, that's partial. If you had the derivative be positive, you have something that was concave up. Oops. And if you had this to be negative, you had something that was concave down. And you can kind of see, oh, concave up kind of sounds like a minimum, concave down kind of sounds like a maximum, even though you can have like differences. But you can kind of see a little bit of the similarities here. Now, when I think about this formula I don't really memorize. What I kind of think about it is I like to write it in a matrix. So kind of like to write it this way. So write f sub xx, f sub xy, f sub yx, and then f sub yy. Where in the diagonal you have the partial derivatives of the same variable, and in the off diagonal I have the mixed partials. And what I do is I just take the determinant of this. So if I take the determinant of this, I get this times this, which is just f sub xx, f sub yy, minus this part. And notice, remember, by Clairaut's theorem, this guys are exactly the same. So you basically have f sub xy squared. And this is actually your d. So I'm basically finding the determinant of this. Again, this formula, I know it seems really funky, and you're probably wondering, where did this come from? I will probably drop you guys a link if you guys want to take a look at it. It is a little sophisticated, and it does involve a lot of linear algebra. If you don't have that, it might be really difficult. So this proof is a little sophisticated, but all we need to know how to do is how to use it, okay? All right, so that's a little bit of the explanation. In the next video, what we're going to do is do a couple of examples to kind of be able to classify all these things.